Here indicates that this implementation is using a regular commercial hardware. And the green line here means that it uses supercomputing equipment, very dedicated equipment specifically optimized for the graph computing engine. So you can see when the scale is very large, and then most of the most of the systems use those supercomputing. So one project we did in Huawei is that we want to do a graph computing engine. We want a large scale, but we don't want to use supercomputing equipment. Instead, we just want to use the regularly available facility to servers to build our system. So this is the architect we use we call it EVA in the Huawei. And we just launched it this month, early this month. And the system can handle the graphs of over 100 billion edges and 10 billion nodes in that scale. And we can answer the 3 hot queries in seconds. Okay, I will show you the performance result in a few minutes. And also, on this platform, we can do all kinds of graph algorithms. For example, some of the algorithms we are implementing, including with those continuous inference maximization, dynamic inference, node checking, and so on, which can support applications such as fraud detection, real-time recommendation, social network analysis, and marketing. So this is a very good combination for me because this part of work needs a lot of hardware and money. So it would be good to do it in a company. But for algorithm development and research work, indeed my team at SFU can help because the graduate students, they give them the machine, they can always turn that into great research papers and algorithms, and then you just need to stir the algorithms and then ask the engineering to tune it better than you can run on your system. So, limited by time, and also I think this is a general audience, so I won't go into details about algorithms, but if you're interested, we can talk about that. The real challenge here is that because the graph is so big, like we can do 100 billion edges, you cannot put the whole graph into main memory. You have to split the data among different servers and let the servers connect it. And also, you have to handle concurrent queries. In this example, we handle 100 concurrent threads at the same time because this will be used by many users. So for partitioning the data into different shards, indeed there are 2 purposes. One is for redundancy and reliability. The second is for high availability. So we need to partition the data in the way that the access to jump among different shards is minimized. So our design essentially is we use some heuristic approach to partition the data and make the redundant copies of the data in different servers so that it can be processed efficiently. Okay. Yeah, this is sort of our algorithm how to do this and divide the tasks into different types so that we can accommodate those tasks in the system. So, but if you look at this is the performance curve, you can see that this curve is the query on the largest data set, 100 billion edge graph. And you can see most of the query, over 90% of the query can be answered within 2 seconds. And only very few queries have to jump into among different shards so that the query time is a little bit longer. And most of them can, almost all of them can be answered within 5 seconds. And then for the smaller graph, the performance is like this. And you can see, indeed, the system is pretty scalable in the sense that if the data set size increases dramatically, the response time does not increase a lot. So this is, and here the workload is a uniformly random workload on the query. Essentially, is that we produce a synthetic graph using the graph method framework generator, and then we randomly pick a node, and then the query is we need to return the 3 hot neighbors of the query node. So in the industrial setting, indeed, the applied AI workflow will be from data and then to analytics, and then the general purpose machine learning, which is a very hot topic nowadays, and the domain-specific AI. Well, nowadays, people focus on these a lot. But if you look at how the company can make revenue on such a whole process, interestingly, on data, essentially we sell the resource consumption. And resource and analytics, we also sell the resource consumption, and also the general purpose machine learning, we are doing the same thing. So no matter in Amazon or AWS or in the different kinds of public clouds, the major purpose to make a general purpose machine learning application essentially is to boost the use of resource, and then it will land revenue on data and analytics part. This is generally supported by the cloud. So the next step, is really on moving the general purpose machine learning to domain-specific AI, so that we can have more customization here, and we can have the major value added here. So that if we can move here, then the new revenue channel will be open here. But this needs a lot of domain expertise and a lot of specific applications. So this is a real challenge. In order to support such a scenario, one platform we are building now is that we try to connect the data, the domain, and AI, and end user. At the lowest level, we will build a computational platform, often on the cloud. So this will include all kinds of hardware support, like the general purpose CPU-based servers, the GPU, FPGA server platform here. And on top of that, we will have the general purpose machine learning modules such as translation, object recognition, natural language processing, speech recognition, OCR, and so on. And on top of these, we will support a whole set of domain-specific AI, including, for example, manufacturing, finance, healthcare, and medical things. And so that those ISV integration service vendor and those domain solution developers can build their solutions on top of these domain AI services to meet the needs of the end user. So this is the whole structure or architect of the AI platform. Using such a platform, indeed, we can do a lot of things. For example, one thing we started from 2010, working with Blue Cross. We formed a Pacific Blue Cross Health Informatics Lab. We develop all kinds of solutions to connect different parties of the healthcare. So we work on a lot of data, medical and health-related data, and we try to get the medical and health AI tools. Essentially, we look at patients, service providers, government, and administration, as well as medical insurance payment in the whole cycle. Some projects we work on, for example, is like a fraud detection. And when people make claims, whether there's any fraud there, the frauds may be caused by patients, may be caused by service providers. And also we work on things like drug trafficking detection. Because drug trafficking indeed is a serious issue in the medical system. It costs the insurance companies a lot of money every year. And also we work on the policy verification, meaning a few medical policies were developed in 60s or 70s. Nowadays, with the new technology, those policies may be out of date. But when you decide to outdate one policy, you need the data to justify that it is already outdated and should be replaced by something new. So this is another interesting thing to do. For example, one interesting scenario is that last summer, in Vancouver City, the firefighting department reported they see a lot of overdosed drug user on street. Because if a drug user overdosed and have some problem on the street, they typically will call 911. And 911 has a very limited resource on ambulance. So quite often they just send firefighters to there. I think in New York, in the States, that's the same thing. The firefighters, ambulance, they typically have similar configuration and training on treating emergencies. So the government wants to know why. Why this summer suddenly we have so many overdose drug users on street? So these kind of problems, definitely you need data to work on that, and you need data from multiple sources, not only from the hospital but also from the policemen, like the underground drug trafficking, those channels to get the data. And also we work on another interesting project is that on the long-term, short-term disability prediction. For example, when one person, this is indeed is a very interesting story. One person enters hospital and decided, unfortunately, she or he has to stay in hospital for tonight. And then she automatically enters a short-term disability period. And the service provider, the patients themselves, and also the government are very interested are very concerned, sorry, I should not use the term interested, are very concerned about, when the patients can be recovered. Or in the unfortunate case, the patient may have to enter a long-term disability option, so that many social work and all those things may have to follow up. So this is an important issue. And at the very beginning, we think that those are all medical related, so we load all the medical data into the system, and it doesn't work. No matter you use deep learning or shallow learning, it doesn't work. And later on, we indeed add a lot of social data into the system, and we find out something very interesting. One thing I can tell you is that, one very good example for women, after a lady gives birth to a kid, the lady in medical term indeed is in short-term disability. Sorry, this is nothing discriminatory. Just say it's a medical term, okay? Because the lady won't work for a while. But surprisingly, for some people, they can recover very quickly. For example, for the people in the States, they're very strong. They typically recover in 3 months. For people just cross the border in Canada, they're much weaker. They need 1 year to recover. Why the difference? And from the medical point of view, you cannot explain, because there's just no symptoms saying why. Just cross the border, people become much stronger. And if you look at the social data, you didn't know, because the policy say in Canada, the maternity leave can up to 1 year. And in universities, faculty can get 95% salary in this year on maternity leave. That explains. And well, when you get 95% salary, you don't need to go to any meeting. Yeah, you just stay at home. Okay. So another thing is that for some people, like the CEO of Yahoo, she got the maternity leave only for 7 days. And indeed, from data, we can see that for those executive level employees, their maternity leave is much shorter than the other. Yeah.
I was actually there as an intern. She didn't show up for 2 months, even though she got like.
Oh, okay. Okay, sorry. Our data may be wrong. Well, but at least from the media is that she go back to work. I mean,
working from home.
Yeah, she was working from home.
Maybe. I mean, anyway. So there's something very interesting.
From home, isn't she famous for wedding working from home?
And also, it is very interesting to look at, for example, the role of union in such cases. So it's a very sophisticated data study becomes interesting there. So this lab does a lot of things there. And so essentially, if you look at the opportunities in health and medical, using the data science and AI tools, well, we can do things like assistance in disease diagnosis and health management and disease prevention. And also the patient management, the epidemic alert and drug management, and policy assessment and improvement. All those things can be done. Another interesting example is that, well, indeed we can provide one kind of service is for a company. We can predict in the first week of December how many employees may likely call sick in that week. We cannot tell exactly who will call sick, but we can give some aggregate numbers. This is very helpful for big companies to plan for their HR. Yeah. So the business model there is that we try to do the task optimization and automation. And again, the process optimization and optimization remains a big challenge. We can do things like data or analytics as services. But we can provide services as a product. Sorry, the title here. Essentially, if you have the data, you just want to use the analytic tools. So you can feed the tools with your own data. We can keep everything private to the user. Another thing is that for customers having no data or not enough data, we can use the data and services as a product. For example, the example I just talked about is that we can predict for a company how many people may call sick in the first week of December. And for such problems, using your own data typically is insufficient. You need a much larger data set. You need the regional distribution, all those things. And another important, interesting case I would like to mention is one of the big projects I started last September and got quite successful in the market is on the supply chain optimization. And well, we all know supply chain is a very, very long chain, including from manufacturer to material storage, factory, EMS, and shipping, and at the end to the customer. Okay, and we use many steps in the supply chain as examples and motivations in optimization problems again and again. However, in most of those optimizations, we only focus on one step. For example, we do like cargo planning. You have that much boxes. how to put into a truck, how to put in a cargo so that you can fill the space as much as possible with some constraint is that the cargo has to be balanced, right? You do these all kinds of things. And you do the route selection and optimization so that you can minimize the shipping costs or something. But when we do these, when we work on these for Huawei, we are facing two problems. The first problem is that the supply chain is a whole chain. Indeed, optimizing on one step can help, but cannot solve the whole problem. For example, when you do the cargo planning, and you assume you are given a set of boxes to put, right? But those boxes belong to different customers. If your route selection are different on the next step, you'll end up with different boxes in the previous step. Because for the same set of customers, you may have different routes, send different trucks to ship the things to them. Okay? Then how to make the optimization connected in these two steps is a problem. Is a big challenge. And also, it is related to time, because for some goods, you have to send it today. Otherwise, if you send it tomorrow, it will be late for the customer. And then the customer will complain, you have to pay for the penalty. But for some goods, you don't need to send it today. If there's space, you can put it in. If there's no space, you don't need to order a new truck. Instead, you can just let them wait for one more day. It doesn't really matter. So this is another issue. And there's some more issue like very sophisticated is like a custom. When you ship things to overseas, you go through the custom. And particularly if you are filling a warehouse for items not sold yet. Well, for example, you have 100 things to sell. You have a stock for the things there. Okay. At that time, you don't even have a price for an item to sell because it is not sold yet. It's not on contract yet. You just fill the local warehouse, and you still need to file a custom claim here. And then you need to be careful. You don't want the price of your claim up and down too much. Otherwise, you will be subject to inspection. Once the inspection, there will be a long delay. Okay? So a lot of things, for each step, you know more or less how to optimize it. But when you're connecting multiple steps, then you suddenly realize my optimization algorithms cannot handle that sophisticated situation. And at the end, the problem is how well the data, the information is connected among different steps. Okay? When I do these, for example, a simple solution is that you can do sort of like a heuristic. I do a little bit of optimization here, and then I can query the next step and the previous step, say how much space I can go on those steps to gain a little bit better, a little bit flexible setting. Then it meets the data problem. Okay. And the second question is, well, different companies have very different supply chains. And when we talk about the major issues, they are similar. But when you look at the special issue, the configuration is so different. So in order to solve the problem, indeed, we developed a whole set of services. For each step, we developed some services. Each service can be configured using parameters. And then a user indeed can use those services to assemble their own solution. In other words, now we don't provide one solution. Instead, we provide a platform of services. Whenever a company wants to have its own supply chain solution, he can just pick the services he needs and then assemble them and add the constraint, add the logic, and then to make his own solution there. But the whole thing is honestly, not really research or not really academic research oriented. It is more like engineering work. If you open every box, what we use is very simple, like a heuristic approach. But altogether, how to make it, seamless connection with the underlying data is the real work we done. So, in general, I really appreciate the my time here. Really, I started my academic research, mainly focusing on data and the data science, data mining, this part. And my further experience in more industry-related research and development really tells me that, we as the data and data mining, machine learning researchers can help to build the AI platform and services, but we need to link with data scientists, with domain knowledge, AI technology, and also domain applications and the user to form the whole basis. But the good news is that the whole foundation is still on data and the applications of data. Okay. So probably that's all I want to talk today, but I'm very happy to answer any questions and also take your suggestions and comments. Thank you.
Professor Tai, it's a very interesting talk. And I'm interested in particular one slide you showed your time series to predict.
Yeah.
And also that another slide actually from that machine learning model to domain specific problems.
Yeah.
I had actually a problem before to that. For example, climate simulation, climate model.
Yeah.
And then for to predict the future, you can use a very complex physics model to calculate, to simulate the future.
Yeah.
On one hand, you can actually use the sensor data to predict what the future looks like.
Yeah.
They might agree, they might don't agree.
Yeah.
So that means that you have some sort of methodology sort of unify them, allow them to actually refer or reference or cross-check each other. That's question number one.
Yeah.
Question number two is that how that actually the complex physics model, which actually you can bring early in your machine learning, and then your engineering of your time shares, which actually sort of like, okay, I directly give you the result, trustworthy by the climate scientists.
Okay, maybe let me answer your second question first. Okay, the second question indeed is what we've done in this series, whole series of work here. Essentially, the intuition is very simple. You have a model, okay, and then if you take less data to make a prediction, you look at whether your model works in the same way. If it works in the same way, the prediction results are similar, that means indeed you can do earlier, right? And then you move earlier further. Okay, so you do this all the way until you see your model cannot work, cannot be moved early any further. Of course, in this process, we can reduce the redundant computation because if from t-1 to t-2, the prediction process, a lot of computations can be shared. Okay, that's a major sharing. So and after that, we try to look at different features. Those features are sort of like pertinent in time, can give you more informative signals on the prediction. So that's the reason we write more than one papers on this thing. Okay. So that's the answer to your second question. You have to move it forward. For the first question, indeed, that's the big challenge. That's something we could not done. Is that after we get this model or this method, we try very hard to find real applications that we can really test the data, and we failed. Maybe is that we needed them. Well, you can always produce some synthetic data sets, or even you can use some pseudo, or semi real data sets to do that. But at the end, we cannot make a real killer application to solve the end-to-end solution. And this really motivates me to understand that interdisciplinary collaboration is very, very important. At the end, you really need the medical people to initiate the projects to solve their own problem. And by the way, they find our tools are useful. So I don't have answer to your first question, but I know the direction is that you probably need to, sort of like you are the salesperson. You cannot say this is my tool, you work on my problem. Instead, you are a salesperson, you talk to different users, and by the way, what if you use my tool? Sometimes it may help you. And if some of the customers take your products, then you show it is marketable.